Welcome back to Tetryonics. In this video we'll cover some basics of physics, such as the spatial coordinate system created by light as it propagates through space itself, and the equilateral mass energy momenta within those spatial coordinates. How the geometry of energy leads us to mass within spatial coordinates, how space itself is mapped out using a coordinate system generated by the direction of light. We'll differentiate between scalar and quantized mass energy, classical physics and quantum physics, and we'll touch on subjects such as quantized angular momenta, square root linear momentum, acceleration and the forces that bring acceleration about. Empty space, that is a region of space that has absolutely nothing in it, must be defined in order for us to map or measure physics within that region. Doesn't matter what units of time you use or how you go about mapping it. In fact, there are several different coordinate systems that are in use that have been developed historically over time. In Tetryonics, we base the coordinate mapping system on the propagation of light. In the center of the illustration you can see a photon, a plus and a negative boson, a dual boson, which is a photon of energy that radiates out from a source. By mapping the direction that the light beam radiates out, we can develop a number of spatial coordinate systems. The first and foremost is a linear one, where light propagates out in a direction. Any of these arrows pointing outwards from the source is a linear propagation of a beam of light in one direction. Think of a torch beam pointing outwards. Using basic geometry, pi r squared, where r is the radius of the circle, i.e. the beam of light that we've just discussed, we can then create circular spatial coordinate systems based on that beam of light. In the case of a single beam, C, the beam of light maps out in a unidirectional path. With that path we can use that to map things such as force, accelerations, etc. It has obviously the units of C, and it has time units of light seconds, i.e. how far light will propagate from a point per unit of time, or per second. So light seconds, very similar to light years that you hear often in science, but in this case we're using seconds. There's no reason why, if you wanted a quantum view of a system, you would not use light milliseconds or light nano or femtoseconds. It's simply an easy way to do it. And in using seconds, it rationalizes the physical units back into c squared, etc. With respect to c squared, photons propagate in actuality in two directions. A torch beam has a reflector that forces the light beams to go in one direction. But light from, say, a candle source or an arc lamp will radiate in two directions at once, the plus and minus energy momenta of the photon. In doing that, the single beam of light is now, or the single radius is replaced with a double radius or a diameter, again per unit of time, creating a circular coordinate system, or c squared, two beams of light. Continuing this through, you could have three beams of light forming axes of spatial coordinate systems, c3, and these could point in x, y and z directions to create the Cartesian or rectilinear spatial coordinate systems, x, y, z, that everyone's familiar with from classical physics. Or alternatively, you could have a beam of light radiating left and right on the page as illustrated, and a second beam radiating up and down from the page at the same time. that would then form four axes, a quadrature wave, if you like, a plus and minus x, plus and minus y, four axes, c to the fourth. Of course, with the two diameters being orthogonal, you would then map out a spherical region of space in which to observe the physics taking place within that region. Obviously, the region that's mapped out per unit of time is determined by the speed of light in this case. I chose it because it rationalizes the units when you look back into relativistic mechanics, and it also brings about a lot more coherence and understanding when you encounter units like c squared and c to the fourth in physics, as well as c to the third in entropy and things like that. This then explains those units as not just a number or the square of the speed of light, which often raises eyebrows, but shows that it is in fact a light cone. C squared, for example, produces a light cone over time. So in 1 second, the circle might be this large. In 2 seconds, it's expanded out because the light is propagating out at the speed of light. 3 seconds, it's grown to this size. 4, 5, 6, 7, 8 seconds. As that circle expands over time, it creates the light cone that's so familiar within relativistic mechanics, at least. This is how Tetryonics defines spatial coordinates. It does so by the speed of light in any region. Now obviously the speed of light can change, and we'll touch on that shortly. But for the purposes, it gives us a unit where we can say easily things like energy per light second is E divided by c squared, giving us mass. So mass then becomes a measure of energy in time. Take away the time, take away the circles in Tetryonics, and you just have energy. And this is where the geometry of Tetryonics starts to play an important and very functional role, in that we can start to draw and illustrate terms like c squared, terms like, and be able to differentiate between mass and matter, and mass and energy, despite them having very similar properties and features. In the case of a single beam of light, or C, we can obviously map out linear meters, because the light propagates at the speed of light in 1 second to 300 million meters, just under, in that time. So we can use that linear arrow or linear axis to measure vector forces, acceleration, deceleration, etc. As I said, c squared, so familiar in E equals mc squared, or which can be rewritten as m equals E divided by c squared. The c squared, that's so hard for most modern physicists to explain, is in fact nothing more than a spatial coordinate system mapping out the region of space in which the physics is taking place. It's just establishing a box or a sphere in which we're measuring the physics, or in which the activity is taking place. And of course, radial light seconds equals c squared. So we can use these circular coordinate systems to measure things like mass, energy, and obviously linear momentum, because one-dimensional can be contained within two-dimensional. It's just another axis within the two-dimensional axis of c squared. But you can't measure a Cartesian coordinate system nor a Quaternion system, because you can't contain C3 or C4 in a lower ordinate coordinate system, but the reverse is opposite. So if you were doing classical physics, you could rewrite Cartesian coordinate systems x, y, and z as c to the third, or c cubed. And obviously relativistic mechanics with space and time, etc., they can all be mapped out within c to the fourth. So we now see that the Cn coordinates, or the Cn's that you see in physics, actually relate to the coordinate systems of the spatial regions. And within them, it's just an empty space. It's only bounded by the time that it would take light to cross that or to bound that region of space that you're defining. Within that region, all the activity, all the physics that takes place is created by equilateral mass energies. The equilateral mass energies create force, they create matter. Matter contains mass energy momenta. And this is where it becomes crucial again, as I've discussed previously, to be very familiar with the differentiation between two-dimensional mass energy and three-dimensional matter. But throughout all of physics, or throughout all of Tetryonic physics at least, the moment you see V divided by C or V squared divided by C squared, etc., as soon as you see the C squared, C cubed, C to the fourth, you can immediately think of circular or rectilinear coordinate systems. That's what it represents. The geometry of energy itself, as I mentioned before, is equilateral. That's determined by the quantized angular momentum of Planck's constant. So the scalar, the area, the surface area of any energy, or any quantized or scalar energy, is the surface area. So you can see here we have an equilateral surface area. Starts off at, following the Tetryonic coloring system, purple for the highest energy, and over time, as the energy itself spreads out, it gets weaker and weaker, following, not unsurprisingly, the inverse squared law. Even though the terminology is inverse squared, it is in fact an equilateral geometry spreading out. Again, what mathematics calls squared, Tetryonics immediately shows you is equilateral. Interestingly enough, the equilateral geometry of Planck's constant, or any equilateral, is the inverse spatial geometry of a circular, or of a circle. So per unit of time, as the triangle within the circle in the center spreads out, 1 second, 2 seconds, 3, 4, etc., the circular coordinate system expands accordingly, as does the energy at the inverse of the square. And of course, as it's the inverse of the spatial coordinate, whereas the circle is c squared, or light seconds, if you were to measure the energy content within that light second coordinate system, it would of course be the inverse of c squared, 1 over c squared. That's another way of saying energy divided by c squared. E divided by c squared equals mass. So there again, you can see how energy can be measured, or is another form of mass. The only difference between energy and mass is the circular coordinate system. And the coordinate system is determined by the speed of light propagating out. In this case it's c, but the speed c can vary. Everybody thinks of c as the velocity of light, and it's a fixed velocity, 299,000 meters per second. When light passes through water or through glass, for example, that value changes. So c is not a fixed value. C is just the speed of light in a medium. So it's the velocity of the light is determined by the medium it moves through, and again, the medium is simply the electric and magnetic permittivity and permeability of the region. Big words, but it's just simply how it's the electric and magnetic properties of a region of space that, when light encounters it, determines how fast it can move through it. akin to the Higgs boson when they talk about it, but it's a different mechanism. It's simply, what we're alluding to here is that any region of space in our universe has energy in it. The vacuum energy, as it's often termed. That vacuum energy is made up of electric and magnetic fields, and as energy tries to move through that region, the electric and magnetic fields of the vacuum energy determine how fast light can propagate. Just so happens that the speed of light, c, that most people assume is that fixed value, is more appropriately termed the speed of light in a vacuum, or the speed of light in free space. You'll often see it termed as. Again, it's just energy trying to propagate through more or less dense amounts of energy. In the case of a vacuum, it's a uniform energy field that it's trying to propagate through. That is what is allowing light to propagate from one star to the other. The ether, if you like, the vacuum energies. Again, they are all equilateral, whereas the spatial coordinates are circular. So how do we apply this to basic physics? Let's run through a few basic terms that you'll come across in physics. Things like velocity. It has units of meters per second. It's a vector force. It's a vector direction. You're traveling in a direction for X amount of meters per a set amount of time. In the case of the illustration here, we can simply put the apex as the starting point of an object, and it travels in that direction, that distance, per second, light seconds. If you measured the energy, the M here stands for meters, if you measured the energy content that an object had in order to move, you could then calculate the mass of that energy. But again, the simplest part here is that we have meters, linear meters, per second. And that acceleration, the force that creates that acceleration, is created by the equilateral energy that's available in that region of space to create that force. So it's the equilateral energies and their square root linear momentum that creates the vector velocity. And you'll see terms like this coming up, and it'll become more familiar as you grow. As you get more familiar with Tetryonics, you'll grow more accustomed to thinking in these terms, and things will become a lot simpler because you now have a visual aid to the mathematics. For example, acceleration, which often causes a bit of consternation between students of physics, with units like kilogram meters per second squared. Per second squared often has the same result as c squared. What is c squared? How do you square a second? Well, we've already covered that with the quaternion 4-axis propagation of two beams of light. You can now see that second squared, or light second squared more appropriately, is in fact c to the fourth. It's a spherical region of space where a beam of light propagates in two directions one way, and at 90 degrees it propagates in two directions, left and right, up and down, to create a circular region of space. A bit hard to draw in two dimensions, but I hope you'll get the gist of it. Within that region of space, that's c to the fourth, light second squared, there's the second squared that everyone has trouble with and trouble explaining. Within that region of space, we have energy. And that energy, of course, can create a force. Energy has units of square meters per second squared, kilograms square meters per second squared. That's the units for energy. So another way of saying that would be mass velocity squared, or mass equilateral area per squared second. Not always easy to explain, but you basically have a circular region of space where the equilateral energy, kilograms square meters per second squared, creates a force in one direction. So then you then have mass, meters again, just a vector force in one direction or the other, per second squared. And there's the second squared. It's really light second squared. That force, and for those of you that listened to the previous web recording, you'll now notice something familiar popping up. That force can accelerate or decelerate. It can speed things up, or it can act to slow them down through the application of force or a changing force. A constant force would not accelerate or decelerate. It would just produce a uniform motion. But where energy is added and removed from that equilateral triangle, you can either achieve accelerations or decelerations. And the energy is removed in odd-numbered quantas, bosons, W bosons to be precise, but bosons, odd numbers. And again, 2n minus 1 or 2n plus 1 is the definition of an odd number. So in this case, instead of n's, we have velocity, because we're changing velocity through the changing number of quanta within that energy field. So simply by removing 2n plus 1 or 2n minus 1, or adding 2n plus 1 Planck quanta to the field, we increase the energy that's available, which increases the linear force and increases the acceleration. If we take away an odd number, a specific odd number of Planck quanta, we reduce the energy. The number of Planck quanta that are left is less. The force that they can exert over a distance is less, and therefore the object will decelerate. So that leads us directly to Newton's laws, principally his second law, F equals ma, where a force acting on a known mass will cause an acceleration or a deceleration. So acceleration is just a measure of a force per unit of matter or per unit of mass. So all these complex terms and confusing units, such as second squared, light second squared, c squared, etc., all these sort of things can now be rationalized visually, explained, and you can see how energy leads to force, leads to accelerating objects, leads to changes of velocity due to changes of energy, and how we can measure that energy per unit of time to give us a change of mass, as Einstein predicted. Increase the energy of a body or its speed of motion, and you're increasing its mass accordingly. It's a direct relationship, and it's a constant relationship. As you increase something to higher and higher velocities, you must use more and more energy in order to achieve that acceleration to the next highest level. But there is no limit. Unlike relativity that says that the speed of light is the maximum speed, the equilateral geometry shows us that there is no limit. Provide sufficient number of Planck quanta in a region of space, and you can accelerate an object to any speed. We'll discuss that later for those that are interested, or you can message me on it. We'll go into much more detail if you want. The linear momentum should not be confused with quantized angular momentum, or indeed classical angular momentum. They are three distinct things. Just to recap, linear is a directional vector force. Angular momentum, as classically explained in physics, is a rotation about a point. Where I've highlighted there, imagine that being a point in the center of an object, and it is then spun around that point. That is angular momentum. It's measured in square meters per second. That's its SI units in physics. And it can be termed a number of things, but in the macro scale, in our scale of the universe, we call it angular momentum, UM. I use the UM to differentiate it from momenta, which is a quantization of momentum. Same units, and this is where it gets interesting, so strap in. Same units, square meters per second, which you find in Planck's constant. Kilograms square meters per second is Planck's constant. The same units at the quantum scale mean something entirely different. No doubt you've heard of terms like quantum spin. Some of you more familiar with electrical engineering would have heard of terms like flux or curl of electric and magnetic fields. All these terms at the quantum scale, even though they have units of square meters per second, are not measurements of a rotation about a point. And this is a major redefinition of physics. And this is what you have to wrap your head around very precisely in Tetryonics. In Tetryonics, quantized angular momenta, QAM for short, or omega, that's the unit for it, omega, is in fact an equilateral geometry. Again, the equilateral, which can measure vector meters, linear meters, also has an area, a scalar area of square meters. A triangle can measure square meters just as a circle can, just as a square can. In quantum physics of nature, nature uses equilateral triangles. Odd-numbered triangles add up to form squared-numbered energy levels. This is all covered in the previous discussion. But this is the break from modern physics theory that allows us to visualize particles and fields and allows us to unite quantum theory with classical physics, with relativistic physics, to bring together quantum theory, to bring together electrical theory, chemistry, biology, cosmology, and even math itself. Of all those theories can now be brought back together through the visual geometry of equilateral Planck quanta. So what it says, in what I'm saying in essence is, where you see Planck's constant, you should visualize this: an equilateral chunk of energy per c squared. E divided by c squared is mass. The equilateral geometry is meters or square meters per second. So Planck's constant, that is a visual representation of Planck's constant. In fact, Planck's constant is also commonly referred to as the quantum of energy momenta. It's the chunk of energy that allows energy to create force, momentum. Again, the momentum is contained in the apex of the triangle, predominantly within the electric field. But this illustration is the key illustration for Tetryonics. This is where we depart, or where it departs, from physics as it's taught now. You can still term things as spin and as curl and as flux. Positive and negative charges, for example, are just they spin one direction or curl the other, clockwise or anti-clockwise, as illustrated here, to create positive and negative charges. But Planck calls these quantum oscillators. They don't, in the technical sense, oscillate. The energy flow is always in one direction if you're modeling these triangles as an inductive loop. Electrically, think of an inductor with a coil at the bottom and the leads lead up to a battery at the top. The energy flows through the coil and back to the battery, creating a magnetic field in the coil. It'll have a north or a south direction depending on the direction of energy flow or the polarity of the battery. or even the direction of the winding. But what is termed as a flux of energy or a curl of electric and magnetic fields is in fact the result of equilateral Planck geometries at the quantum level. There is no physical spin, there is no curling, there is no flux going on, although we can use those same things to build macro scale devices based on these geometries. And in fact, part of Tetryonics in the experimental sides will be to build devices based on the information that nature provides us through this understanding. So with the scalar Planck quanta building up, as you can see here, a number of Planck quanta, odd numbered bosons counting across or in the transverse fashion, sum up to give us squared number or equilateral number energies within that equilateral geometry. Again, the equilateral geometry is square meters per second. Square meters per second. Per second is the circular coordinate system, giving us energy per c squared, mass. Mass velocity is linear momentum, mv, p equals mv. mv squared is energy, as it's taught in classical mechanics. Interestingly, the argument between Gottfried Leibniz and Sir Isaac Newton over the years was because Sir Isaac Newton dealt with force and acceleration, changes of linear momentum that are brought about by changes of energy content in a coordinate system. The energy content is what Leibniz was describing vis-a-vis life energy, etc. He was referring to the scalar. Newton was referring to the vector or linear forces, or the vector forces that result from linear momentum. Max Planck came along and tried to explain the spectral colors of light from this understanding of scalar energy and linear momentum, and found he couldn't, until he measured the energy content required to produce the spectral lines and divided it by the frequency to discover there was a constant that kept popping up. What was this constant? It's now known as Planck's constant. And simply put, he took kilograms square meters per second, which is energy, and divided it by the frequency, or how many quanta per second in that energy, to come up with a constant. And that constant has, again, units of kilograms square meter per second, or kilogram equilateral kilograms per light second. What's been hidden from us in physics up to date is the fact that Planck's constant h, with its units that we've described, can in fact be described as mass omega. Remember again, mass is kilograms, omega is square meters per second. So mass omega, which is an equilateral geometry, is key to developing Tetryonic theory. In doing so, we then unite Newton with his work on linear momentum, Leibniz with his work on scalar energies, life force, with spectral lines and Planck's heat law. We bring them both together in one simple geometry where mass omega is Planck's constant. The key part is the omega, the equilateral geometry, which has been mistaken for a vector rotation about a point. Or, interestingly enough, in the case of Planck's constant, it's even dismissed as a vector rotation about a point. It's not even thought of as spin. If you ask a professor what the square, if the square meters per second in Planck's constant can be thought of as a quantized angular rotation or a momentum? The answer will be no. Tetryonics gives us a whole new interpretation of what is going on here. It is indeed square meters per second. Mass velocity squared is energy. Planck nu squared, or the number, equilateral number, squared number of Planck quanta in the equilateral geometry, is also energy. They're one and the same. You can unite those two or equate them to each other through omega. Omega is the key part of understanding. The equilateral geometry is also key. You have to put the two together and understand that triangles, equilateral geometries per second, are in fact quantized angular momentum, and it is different to classical angular momentum. We can apply this to all energy forms. Every single form of energy or mass out there is a flat or planar Euclidean XY only. There's no Z component. It is just exactly as you would if you printed the sheet out and cut it out. It is a flat membrane of energy, electromagnetic energies, which can be described either as a scalar form with a linear component, i.e. how Newton and Leibniz described it. It's a equilateral energy that can exert a force to change the motion of a particle or exert a force over time. Or you can describe that same field of electromagnetic energy, momenta, as Planck did by dividing it up into smaller triangles, quantizing it, in which case the formula is no longer mv squared but h nu squared. You'll often see Planck's formula written as E equals nh nu. That's a mathematical way of saying energy is a certain number, any number of Planck quanta. That is only true in certain cases. So far as energy is concerned, it is more appropriate because it is equilateral and there are a squared number of quanta within that equilateral. You can't have a non-squared number in there. You won't make a triangle. So it should always be more appropriately expressed as E equals Planck's constant nu squared. And when you do that, you can then see the basics, the beginnings of my unified theory formula, where mass mv squared is also related to Planck's constant nu squared through omega. And of course, out of this you can also see that linear momentum, mv, mass velocity, is the square root, the height of a triangle, of an equilateral triangle, I should say. If you count, you got 1, 2, 3, 4. You would have 16 diamonds in this. 16, I should say. 2, 4, 6, 8. You would have 64 triangles that are barely visible in this illustration. 8 is the square root of 64. You can geometrically redescribe that to say that mv is equal to the square root of energy. Linear momentum is the square root of energy. Or linear momentum squared, p squared, is in fact equal to the energy. Same thing as saying mv, which is linear momentum, squared, is equal to the energy. So now we're starting to see how we can start to unite and bring back out all these formulas that you see in physics so far as motion, be they classical or quantum, even relativistic, where you see mv squared per c squared. We now know what c squared is. It's a measure of 1 light second. So mv squared per c squared is exactly what we have illustrated here in both cases. It's energy Percy squared. It's mass. Energy per light second is a measure of mass. Mass times the square of the speed of light is energy. They're not equivalent, they are the same thing. What is changing is how we measure them. Energy without a time component is simply an instantaneous ability to do work. That amount of energy, if applied, could do this amount of work. But in order to see that amount of work occur, or to be conducted or engaged, you would have to measure it over time, which brings us back into units, coordinate systems of c squared, or c to the fourth, which then turns energy back into measurements of mass, or you would then measure the action that the energy can do by its acceleration of an object, its changing linear momentum. mv, mass velocity. The relationships all come back around this geometry. The geometry is key, and it's the missing component that's been hidden in plain sight in the units of Planck's constant. Expanding on what I've just said, you can see here that the Tetryonic base, or the base Tetryonic unified equation for bringing quantum mechanics and classical mechanics together, so far as mass energy momenta, as it's often termed, is simply mass omega nu squared. This covers everything we've just spoken about. If you want mass velocity, the classical components, what Newton spoke about, mv. If you want to talk about energy, mv squared. That's the equilateral component. You don't need to, as a scalar, you don't need to worry about its geometry. You just need to know what all the components add up to, what effect they have. Energy, momenta. Planck's insight was to quantize it, to chop it up into little triangles, although he didn't know it was triangles at the time, and nobody did until Tetryonics. But when you chop energy up into mass omega, as illustrated here, you have little chunks of Planck's constant, little chunks of energy, electromagnetic energy momenta, because every triangle of Planck's constant is an equilateral. It has a height with an electric field that can exert a force and a magnetic dipole that does no work but is still present. It can affect the force transversely, Ampere's law, for example. But the linear force is exerted by the electric fields. The linear momentum is the kinetic energy, half mv squared. 1/2 of the mv squared is the electric field. The other half is the magnetic. And this is where Einstein went wrong. In either case, all these properties, be it classical or be it quantum mechanical, can be represented in that simple equation for energy, mass omega nu squared. Or if you combine the units of mass omega back into Planck's constant nu squared, it's just a reformulation of energy. A little bit more complex in some respects, but the utility purposes of having classical and quantum mechanics in the one formulation for energy opens many interesting doors. And again, you can do a dimensional analysis of what we've been talking about here, what I've been talking about, and break it down into units of kilograms, length, time. And you come back to mass in kilograms, square meters per second for your quantized angular momentum, per second, nu squared, and you end up, or per second squared I should say, nu squared, and you end up with the units for energy. Classical mechanics looked at the scalar properties and the force that was created. Quantum mechanics looks at what makes up the scalar to create those forces. What nature uses as a building block in order to create scalar energies that we discovered 4 centuries ago now, and how to bring them all together. So, as I touched on before, we now have a clear picture of what energy is. Energy is an equilateral electromagnetic form. It can be quantized, chopped up into smaller equilateral triangles, or made larger through the addition of more equilateral triangles, providing they are of the right amount. And that right amount is key when you come to Einstein's work function for spectral lines, a discussion that's part of QED and not part here, but it falls into explaining why certain frequencies of light, specific light, are required to increase the energy of electrons, and why you can't just use more and more red light, for example. We can now see that linear momentum is a geometric property of that equilateral energy. In fact, it's the square root, the geometric square root. In the case of a single quantum, it in fact equals the electric field. But once you go above the second energy level onwards, it forms these diamond patterns of photons. It's the linear photons that exert a force on an object, creating the linear momentum of a particle in motion. We can rewrite this, we can look at it via the units, we can look at it via the math, but at the end of the day, we now have a geometry that shows us that the linear momentum of a field of energy is the geometric square root of the quantized angular momentum of that mass energy field. We measure all this mass energy momenta in a spatial coordinate system built up using light seconds. Again, you could use light years, light milliseconds, or horse hours, or any unit you wish. All you need is a measure of a constant motion that doesn't vary over time. Horses obviously tire. Light doesn't, and light travels until it is absorbed. So we can look even closer at that and differentiate between the two forms of momentum that I've touched on previously when I said that quantized angular momentum is very different from angular momentum in the classical sense. Omega is very different to linear momentum. Linear momentum, again, is the square root mv, or mv divided by c in the case of quantum mechanics, in case of relativity. And that linear force, the linear momentum that creates a force, can also be drawn, as I've touched on, using the same geometries. We can see in both cases that the scalar energy, the surface area, the scalar energy, is made up of quantized electromagnetic bits, Planck quanta, and that they follow a formulation of mv squared for the scalar and mass omega, mu squared, or Planck's constant, h mu squared, for the quantized formulation of the same. But the energy within that field is capable of exerting a force, either longitudinally, in the case of linear momentum, to create a velocity, or it can create a transverse force as well through the magnetic fields to create a sidereal force, a transverse force, which is known as Ampere's force. An electrostatic particle, particularly in motion, an electron, for example, moving in a constant current, will create a force on another particle or on another wire, which is measured and forms part of the measured forces of physics, Ampere's law, Ampere's force. Again, all coming back down to this scalar energy and the geometric properties that we can derive from that scalar energy. So we can now equate velocity changes to changes of quanta. mv squared, changes of velocity, changes of linear momentum, to h nu squared, changes in the number of Planck quanta in that make up that energy, that contribute to the quantized angular momentum, the charge of a field, be it positive or negative or neutral. The energy that makes up that field, or the photon, or the electrostatic field, the electromagnetic field, is made up of little electromagnetic chunks of energy, momenta, Planck quanta. We can again describe them classically as mass velocity squared, mass meters squared per second squared, kilograms meter squared per second squared, or we can describe them via quantum mechanics as Planck's constant, kilograms angular momentum per second. How many Planck quanta per second do we have? No real difference. One is just measuring the total and what effect it can have. The other one is measuring up all the little bits that sum up to that total that have exactly the same effect. They are all geometric properties. Of a side note, in Tetryonics you'll often see these circular vector rotations, the inductive loops, as I call them. They are a way of explaining charge in Tetryonics. The flow of energy in an inductive loop at the quantum level in one direction or the other through that loop, that inductive loop, will create a magnetic dipole with an electric component. That's drawn using these arrows. Clockwise is a positive charge, anti-clockwise creates a negative charge. There's more complex nuances than that, but that's the basics of it. Throughout quantum mechanic explanations, you'll see me use these on and off. But they relate back to, as I've touched on, omega. You can swap one for the other. The electromechanical engineers out there will see these loops, and if they view it as an inductor at the bottom with a battery at the top, a short-circuited inductive loop, they will understand where charge comes from, and they'll be able to relate inductive mass to inertial mass in physics, electrical to physical. Key part of uniting electromechanics to quantum mechanics. Again, what mathematics attempts to describe using the math and the symbology of mathematics and fails, Tetryonics brings into reality. Tetryonics illustrates what mathematics is trying to describe via its number and symbology. There is a physical, diagrammatic way of drawing mass, energy, momenta, and explaining all these terms, as I've just done, using Tetryonics, that mathematics alone cannot do. And in fact, mathematics, pure mathematics, up to date, has tried to do this and unite classical with quantum, and has failed on many levels, because there's no room within the mathematical language, the constructs, to differentiate between mass and energy, or mass and matter, quantized angular momentum, and classical angular momentum on just a number of points. There's many, many more points where it fails to address and explain things clearly and differentiate one from the other in order to bring about an understanding. Tetryonics shows us the energy momentum relationship, the square to the square root. That's so obvious within the mathematics. yet fails illustration and drawing. Interestingly enough, classical or current relativistic mechanics will draw energy using a right-angled triangle and attempt to explain all these properties and relativistic corrections using a right-angled triangle of energy, and it doesn't work. It ends up producing the erroneous assumption that the speed of light cannot be broken, when in fact it can. Again, all these properties of mass omega, which you'll hear me reference Planck's constant with time and time again, because it is now thoroughly ingrained in my head that mass omega means kilograms square meters per second. Planck's constant is just a letter chosen to represent Planck's constant. Mass omega is literally more correct. This is where I bring about statements like omega is the hidden geometric property of energy, that it's hidden within the math. The mathematics gives you h and h bar. It doesn't give you mass omega. It gives you that in the units for that. Yet they use the symbol, and by using the symbol, they can't illustrate the relationship that Tetryonics now gives us. Mass omega nu squared is equal to energy, which is equal to mass velocity squared. Energy per c squared is a measure of mass. Mass by c squared is energy. And you'll note that in this case we're talking about energy, so not the mass component, we're talking energy momenta, so there's no c squared units, even though I've put them in there to emphasize the mass, the fact that mass and energy are one and the same. They're just different geometric aspects of the same thing. One, energy is timeless. Mass is the time component of energy momenta. Energy is instantaneous, if you prefer. Again, that'll become key when you go to understand Coulomb's law and Newton's law with respect to relativity. So the important part here, the next important part is that omega, the measurement of omega, quantized angular momentum, the equilateral geometry of energy, per c squared, or omega per light second, geometry per light second, many ways of describing the same thing now that math won't allow you to do. It's too rigid, too inflexible. But now that we have the illustration, we can use these different terms to start to bring in different ways of explaining or elaborating on what's going on. But the measure of the quantized angular momentum in any coordinate system is what gives us charge. Electrically, we measure it as a flux. Quantum mechanically, we call it a spin. Maxwell would have called it a curl between the electric and the magnetic fields. There is no curling. It's a result of the equilateral geometry of the electric and the magnetic fields as they pass a point. As you slide that equilateral triangle past an observer, first they'll see an electric field that grows, and as it starts to shrink down or reduce, a magnetic field suddenly appears that grows. When it reaches its ultimate field strength magnetically, there is no electric field. A changing electromagnetic field is inherent within the scalar of the quantized angular momentum of Planck's constant. If it fluxes one way or the other electrically, we produce positive or negative charges, as I've hinted before. A clockwise flux, diagrammatically, produces a positive charge. One positive, no negative component. An anti-clockwise flux produces a negative charge, quantum of charge. No positive component, but a negative component. It's these equilateral quanta, as I've mentioned before, that combine within energy to give us the charge that we observe throughout the universe. Everything in the universe is charged and is the result of charge. These equilateral Planck quanta, or Planck coins, as I call them, Q-U-O-I-N-S, coins. We have a positive head and a negative tail. Either side of an equilateral triangle or an inductive loop is a differing charge, and when these charges come together, they can form either electromagnetic or electrostatic fields. If there's a surplus of positive charges, it's a positive charge field. If there's a surplus of negative charges, it's a negative charge field. If there's a balance between the positive and negatives, you have an electromagnetic field, not an electrostatic. We'll touch on these in a recording or a couple of sessions further on, how to differentiate between electrostatic and electromagnetic. But needless to say, at this point, with Planck quantums, the smallest chunk of energy momenta available in the universe, we have a quantum coin that has positive or negative charge on one side or the other. And even neutral particles and fields are made up of these plus and minus charges. It is an inherent geometric property of the universe. It's how nature makes our universe. The charge doesn't change with velocity because it's a geometric property. And wherever there's an imbalance between the number of plus and minus charges, the imbalance will seek out other charges in order to bring about a balance. The universe seeks an equilibrium. Everything, all the motion in our universe, the motion of particles, the fields of force, the laws of nature, they all come about because electrostatic charges at the quantum level are seeking to equalize themselves and failing to do so for a number of mechanical reasons, which we'll cover as time goes by. But it introduces a term that I call quantum charges, or quantized charge, which is the quantum, the charge at the quantum coins, versus elementary or net charges. An electron has a elementary charge of -1. It is in fact made up of 12 negative charges. So it has a elementary net charge of -1, but a quantum charge of -12. Now we're starting to get into the real gist of how we can start differentiating charge and energy, mass and matter from one another. We can in fact differentiate mass from matter using equilateral charge. The charge will tell us a lot more about a particle than you ever dreamed possible, particularly so far as its shape and form and how it interacts with other particles. Just as we note down the bottom here, along with charge, we can also differentiate charge, as in coulombic charge, from amperes as well. And it's an area of confusion for and disagreement with electrical engineers. But again, Tetryonics deals with that, and I'll discuss it in more detail in the QED discussions. So the field geometry we have when we bring these quantum charges together, these Planck coins, is rather simple. We have a measure of energy per square meter, energy per c squared, which is mass, obviously. So the energy density in a spatial coordinate system, or per unit of time, per light second, determines the mass or the energy momenta that's available in that region to do work or to create other particles, to exert forces. There's specific arrangements of mass and matter. The differentiation here that needs to be that we start to touch on is that mass is planar. It's a measure of energy per unit of time. E divided by c squared. E per c squared. Energy per light second is mass. They're the same thing. They're not different. The way it's currently explained is actually the difference between mass energy and matter. Matter has form, physical substance. It's a three-dimensional shape. It's the difference between a piece of paper and a cardboard box. Matter is the cardboard box. It has volume, it has X, Y, and Z components, whereas the paper, the mass that matter is made up of, is only X and Y energy momenta. This is where we start to really bring geometry into electromagnetic, or our understanding of electromagnetic mass energy and matter. So what is matter? In Tetryonics, matter is defined as the energy density per cubic meter. Now the cubic meter, as we've touched on at the very beginning of this, we can define spatial coordinates for either as c cubed, in the case of x, y, z Cartesian coordinates, rectilinear, or we can take a more generic, all-encompassing coordinate system based on two beams of light and use c to the fourth to contain our matter, which is what's illustrated. Two beams of light, a bit hard to see the second circular axis, but there's two there. It's a spherical coordinate system, c to the fourth, and the energy density within that coordinate system is the mass of the matter. Energy per c squared is mass. That's a planar version or a planar measurement of energy. Matter, having three dimensions, needs another one. So if you like, you could say it's energy per light second. Easier to say E divided by c to the fourth. This is how we begin to differentiate mass from matter. Unfortunately, mass and matter both start with M. In Tetryonics, it's now a standard where you refer to mass to use lowercase m, and where you refer to matter in formulas, etc., to use capital M. And even in writing the word out, you don't spell matter with a lowercase m, you spell it with a capital M. Unless it doesn't matter. If matter doesn't matter as a sentence, the first M will be a capital M, and the second M will be a lowercase. This becomes critical in your understanding and developing a clear interpretation of the difference between mass and matter as we get into more detailed and difficult aspects of physics on any energy scale. You need to be clear on the understanding of what energy is, what mass is, and what matter is with respect to each other. And you can also see here that in the case of matter, it can take up any solid form. In the case of an electron, we measure the mass as an energy per c to the fourth. Doesn't matter whether it's a positive or negative charge, it's still charged energy per light second squared. And the fields, when a particle's in motion, it's kinetic energies, it's Chem fields. Chem standing for kinetic electromagnetic fields. When a particle moves in either direction, an extended secondary field is created. E equals mv squared. You'd probably be more familiar with the kinetic component. Kinetic energy equals a half mv squared. When a particle moves, it has a kinetic energy. It also has a magnetic moment. That's the relativity part. That's why relativity was invented. The classical explained the kinetic energy. Relativity had to explain the magnetic moment. When a particle is not moving, i.e. an electron, there are no magnetic fields. We'll discuss this in more depth later on. But stationary, an electron or a positron is a pure electrostatic particle. There are no detectable or discernible magnetic fields. Even though they are made up of them, you cannot detect them because of their geometry, their topology, the shape of the particle itself and the fields that make it up. But once it's in motion, it has kinetic energy and a magnetic moment, a magnetic dipole. And it's as drawn here. If it moves to the top of the page, it'll have a south-north magnetic dipole. If it moved towards the bottom of the page, it would produce a north-south. These dipole arrangements, with respect to the direction and of travel and the charge of the particle, become essential in QED, where you're trying to interpret Ampere's law, which produces some rather strange results when the particle is in motion, and in explaining relativity theory in an entirely new way that undermines relativity. But the point here being that C that we began the discussion with forms the coordinate, that the beam of light forms the coordinate, the spatial coordinate system, which we describe as Cn, C for force, C squared for mass energies, and C to the fourth usually for matter topologies. We use this throughout Tetryonics. Particularly, I enforce the use of the word planar geometries for mass energy and 3D topologies or mass energy topologies for matter. And I'll cover this in more detail. We can summarize all the stuff we've talked about so far as the quantization of scalar energy, mass energy, and linear momentum, vector forces, and how Planck's constant makes up all these features of charge, energy, momenta, mass energy momenta, whether it be classically described mathematically or using quantum mechanics using Planck's constant. All of it can now be drawn and illustrated using equilateral triangles of energy momenta precisely. The measurement of omega, the quantized angular momentum per c squared per light second, gives us a measurement of time, seconds. I won't go into it here, but you can see through the units. In the case of mass omega, Planck's constant, per light second, c squared. When you write out the units for Planck's constant per light second, you have kilograms square meters per second by seconds squared per meter squared, which is the inverse of c squared, gives us mass seconds. Positive mass seconds, the positive flux or positive change of quantized angular momentum per light second, gives us positive charges. An anti-clockwise flux, as it's modeled, will give us negative mass seconds, negative charge. These are the quantums of charge. So charge is a measure of the arrangement of Planck quanta per light second. Very similar to energy, whereas energy is the ability to do work via linear momentum. Charge, quantized charged, is the arrangement of those same chunks of energy in either positive or negative amounts to make up the field. Scalar energy is a measure of the ability to do work. Charge is a description of the arrangement of Planck quanta, or Planck coins, in any field. They have, well, Planck's constant has units of kilograms square meters per second. Charge as defined in Tetryonics has units of mass seconds, positive or negative, which relates back to time traveling in one direction or the other, or energy fluxes traveling in one direction or the other. It should not be misinterpreted for the ability to time travel. That relates to entropy, and it is not a function that Tetryonics supports. Sorry for those out here that disappoints. Positive mass seconds and negative mass seconds is or positive seconds, negative seconds, if you're just measuring omega per light second, is a measure of charge. That is what creates charge at the quantum level. That's where it comes about. We model it as a spin or as a curl or as a flux in the mathematics or in the physics models. It is in fact the result of the equilateral geometry. Again, omega, equilateral geometry that is present in any spatial coordinate per light second. Omega per light second, square meters per second per square meters per second squared gives you seconds. Seconds in quantum mechanics or in physics in general is a measure of the changing angular momentum of a system. Some of these terms will be really in depth. If they are, go back and listen again, or by all means message me and I'll re-explain it in a different way, or Skype you with a discussion on how to explain this in more detail so that you can understand it. But if you see omega per c squared, think seconds. Planck's constant, h per c squared, you've got mass seconds. Energy per c squared, you've got mass. All these things come out of simple geometry. This is the basic understanding of Tetryonics. The very, very basics that we're getting into here, uniting classical and quantum theories together, throwing in a bit of relativity, but explaining electrodynamics and force, mass and energy, even matter, charge. All these things have come out of this one discussion. And I hope you can wrap your heads around it as we go, because they are key things. Just as bosons and photons, odds and evens, were key in the previous discussion. And you can see here that the boson appears as a positive or negative charge, whereas a photon is 1 or negative 1. Photons are neutral dual bosons, HF versus H nu. Again, all basics from the previous discussion. I know there's a lot being crammed in, and particularly if you're fresh to Tetryonics, but I'm always happy to explain and elaborate where necessary as to aspects of this and where I'm leading you, because these are all key aspects of understanding how nature works without necessarily even having to do this math. I'm throwing the math in because there are mathematicians that will seek to understand the geometry, and they do so by seeing their existing math drawn, whereas younger students can literally ignore the math and just look at how you put the triangles together. You can even use the triangles as mnemonics, so that where it comes to E equals mv squared as a formula, if you visualize it as that, you know that m is E divided by v squared or c squared, and that energy m by v squared. Likewise, the velocity of a wavefront is its wavelength times its frequency, and the wavelength is the velocity, c, divided by the frequency. All these inverse relationships of wave mechanics and energy momenta, electrical energy with work and resistance, and even Newton's law, F equals ma, for inertial force, can be redrawn as a mnemonic using quantized angular momentum. And if you put the mass, the velocity squared, c and c squared, into that very same mnemonic, and understand that the equilateral geometry is a quantized angular momentum, omega, then you can draw that and you can learn that illustration, and you'll see that illustration pop up time and time again. It is literally the foundation of all of classical, quantum, relativistic mechanics and beyond into Tetryonic mechanics. A unified geometry, or a geometry that unifies all the fields of physics and science, and even sacred geometry, as you'll see over time. You'll see if this was a positive charge and you wanted to draw a negative charge field, you would invert it and end up with the Star of David. There's so much information that's packed into these discussions, and things that I forget as time goes by, that hopefully by doing these discussions I'll elaborate as much as I can. If not, again, I'm happy to discuss one-on-one. To bring it all together, we can now see all the physics units, all the dimensional terms, the SI units, the math, the constants, all the terminology of physics and science in general can now be molded back into aspects or different ways of describing this one same geometry. The geometry of mass, energy, momenta, Planck's constant, mass, omega, mass, energy, momenta. That's why you'll see in Tetryonics mass energy is always hyphenated, because mass, energy go hand in hand. Matter does not necessarily. Masses and energy are both geometries, planar membranes of electromagnetic energy. One is timeless, instantaneous. The other one is in a spatial coordinate system. And matter is a charged 3D shape that we make from mass energies. As these mass energies interact via the charge, omega per light second, as these charges come together and draw together, seeking to equalize the region of space that they're in, they can form photons, or more importantly, in the right conditions, they can form fermions, electrons, quarks, baryons, elementary particles, planets, stars, everything from the smallest possible quantum of energy, mass, energy, momenta, Planck's constant, through to the largest thing, our universe, is constructed of charged quanta. So with that, I'll bring the discussion here to a halt. It's been a rather lengthy one. It covers just one chapter, but it did bring together all the physical units, all the dimensional analysis, the basics of classical and quantum mechanics. Brought them all together using one simple geometry. We've used nothing else except omega, the equilateral geometry. I trust I haven't worn you down or disheartened you. It's all very basic. I've just elaborated it as deeply as I could. Thank you for your time. I really do appreciate it if you've made this far. Again, if you have any questions, feel free to message me, and I'll shoot you back answers and replies directed at those questions. Otherwise, stay tuned and I'll bring about another discussion on the next chapter. Thank you.